Okay, on to the next piece then. Monday. On Monday we covered this concept of something called searching, and I showed you two very common techniques. One was a linear search, and really it's nothing new because that's what we've been using all along. You look at the first element, you keep looking until you find what you're looking for, and you stop. It's actually nothing strange. It just happens to have a name. All right, but then of course I showed you this really clever and rather fast thing called a binary search, which is really, really neat. It can find things very, very quickly. Again, if you're interested in knowing the amount of time, you take a course called Data Structures and Algorithm Analysis. But of course, you don't need to know that information. But the one thing that was very important is you had to know that the list of items you were searching for had to be sorted. And once you have it sorted, well, then you can apply the binary search. In fact, as I showed you with that list of students, we looked at the list and it was completely scrambled. So obviously you couldn't use a binary search, but you saw what I did is I flipped some stuff around by copying and pasting, and eventually we got it sorted. And well, then we could actually apply the binary search. So then the question becomes is, okay, if you can sort something and you can make it find information really quickly, all right, how do we have to actually sort things? Now, the good news is a lot of programming languages these days have sorting built in. It wasn't always like that. The early languages, you'd actually have to do this stuff by hand. And there are some really clever techniques and things built into Python to be able to sort what I'm going to describe as complex objects. And if you take a look at the syllabus, complex objects is what I cover on next Monday. So I'm going to show you how to use the built-in stuff at that point, but I will remind you that there's some built-in things here as well. We'll do the easy ones today. However, before we get there, we will actually look at the sorting algorithms because just like in the world of binary searching and linear searching, sometimes, even though something might be built in, you just can't use it directly. And you might need to actually write an algorithm because you got some complex things. So we cover it. Let me get this started because I believe that the first few slides are probably not coding specific, but probably more about how things work in terms of an algorithm. And then, of course, we'll stop a couple times and we can try writing some algorithms to see how things go. All right, so again, the searching and sorting isn't really part of the book, but we do have the set of appendices where I put all this information, so you can take a look at that for more details. All right, so sorting, the word sorting in the world of programming means to take a list, or an equivalent of a list, and basically put it into either an increasing order or a decreasing order. It doesn't make it more difficult if it's the other way, but what I will show today is just putting things into increasing order, but to put it in decreasing order means the same thing. All right, reasons why you might want to have to put something into a particular order. We do this all the time when we're trying to take a look at results from tests, because having a big long list with like 300 or 400 test scores, the easiest way that we can find out how our students doing is to order it from highest to lowest. And you can start asking questions like, how many students got a perfect mark? How many students almost got a perfect mark? How many students have done really, really bad? But once you put it into order, well, then you start to notice these types of patterns, as opposed to if it's just completely scrambled. Now you have to write programs to go through and tell me how many students did this, how many students did this. So having something sorted is very, very useful, because sometimes people find things easier when things are put in an order. Like, for example, most of the attendance sheets that I print up end up being sorted alphabetically by your name. In that way, at least you know roughly where to look when the sheet comes around. Obviously here you just add your name, but I'm talking about the lab sections. Sometimes you need to find the largest and smallest elements, and of course the cool thing is that if you have a bunch of data and you sort it, the smallest element's always going to be at the beginning and the largest element's always at the end. And you say, yeah, but we have a max function for it. Yeah, but the way how the max function works is you have to go and look at the first element, then check the next element, then check the next element, then check the next element. And if you have a million things in your list, that's basically like a linear search. You have to look at everything. But if you sort it, you just ask for the first position, that's the smallest. looking for the biggest, it's at position -1 at the very end. So it's really, really convenient at that point. And of course, well, it allows us to do these really cool fast binary searches, as we saw we could actually do. Unfortunately, sorting is generally pretty slow for a computer, so you'd want to avoid sorting unless you actually need to. Strangely enough, if you remember when I demonstrated something yesterday, I had a list filled with random numbers that we checked to find out how long it took, and we got a numbers like 5 seconds, and then when I sorted it became like 22 seconds. I did some digging into it, and it turns out the reason why that happens is when you create the list the first time, it kind of gets put together in the same area of memory, and the CPU is very good at finding information that's beside each other. It uses a technique called caching. But when you sort it, it tends to take the data and puts it all over the computer's memory, and that's actually why searching for something in a sorted list was so slow. It's very, very strange. It was completely unexpected. I asked a few other people, have you ever seen this? And they said, no, that wouldn't happen until I showed them. It just goes to show that, hey, we don't always know everything about these languages. Python really does some strange things to try and make things quick for us, and unless you're a part of the development team, you wouldn't actually know. But in any case, sorting generally is pretty slow. It's one of the more time-consuming algorithms, so you don't want to do it unless you're actually going to use it for either printing something or to do quick binary searches. In this course, I show two of the simplest to understand sorting algorithms, and trust me, they are pretty easy as I describe them. The implementation can sometimes be a little bit funny, but hey, we'll do the implementation. I'll write up the code, and I'll try to write some comments or say some comments as I'm going so that we understand what's happening. So the very next page has got a picture of the algorithm, and what I would suggest that you do at the moment is please ignore the algorithm. Okay, so I'm going to show you something, but please just ignore the algorithm. And what I'm going to do, I'm not going to hide it on you. I just want to isolate this thing right here, because I just want to bring it up into our editor. Because this should repeat something that I said yesterday, and I'm going to ask, is that list sorted? Absolutely not. All right, remember, to show that something isn't sorted, all I need is one example, and then if that one example fails, then I can actually say that the entire list is not sorted. Remember what I was doing yesterday? I showed you the algorithm. I said, why don't you keep comparing values one after the other? For example, because of course, remember, computers, you can only compare one value to another. That's all they can do at any particular time. And I could point at 14 and 97 and say, well, if I only look at those two numbers and I don't look at nothing else, are those two numbers sorted? And the answer is sure it is. All right, but unfortunately, if I highlight these and ask you, are these sorted? You immediately say, whoa, no, because I should never have a 97 coming before an 85 because the 85 should have come first. Okay, there you go. That's what we're going to be using in order to detect whether or not something is not sorted. And this is basically the way how the first algorithm I'm about to show works. The idea is pretty straightforward. Okay, got a little animation. Okay, so again, just ignore the code. We can look at the code afterwards. The code should have appeared at the final thing. All right, so here we go. Here is my list. Okay, oh good, it's exactly the same list. All right, so based on what I just said, I'm going to start comparing pairs of numbers side by side. So the very first thing I'm going to ask is I'm going to compare those two numbers right there, 14 and 97, and I'm going to ask, are those okay in terms of how they're structured? And the answer is, yeah, those two are okay. The 14 is smaller than 97, so it makes sense that the 14 is in front of the 97. Good. All right, we continue on. The next thing I look at, and sorry for the colors, I don't even have any ability to change these things. It has something to do with the theme. I'm going to ask those questions. When I compare the 97 and the 85, are those okay? And the answer is no, because if they were okay, maybe if it was 85 and 97, I would have said fine, but it's a 97, which is a bigger number, comes before the 87. This is bad. Okay, so what are we going to do? I'm going to fix it. How do you fix it? Well, you take the value 85 and you put it over top of 97. You take the number 97, you put it over top of the 85. Usually you have a third variable you use as a temporary parameter. And if you're looking at the code, you'll notice it. But all I'm going to do is I'm going to switch the two. Okay, I'm all finished, right? Oh, no, there's a lot more stuff I have to go through. You see, I have to continue all the way through. I have to look at those two right here. And again, sorry for, I don't know why the color keeps changing, but anyway, 97 to 77, is that good or bad? Okay, that's bad, so what are we going to do? We'll switch them. All right, so and now it's better. Okay, are we finished? No, we have to keep going because now we have to check the 97 and the 95. Again, bad situation, so I'm going to flip them around. And I have to keep going, so I check the 97 and the 18. Once again, we've got ourselves a problem. Flip it, and I have to do it once again as well, and I have to check, okay, 97 and 90, yeah, problem. So therefore what I'm going to do is I'm going to switch those. Okay, I'm perfectly finished, right? Oh, no. The array still, or sorry, the list still isn't sorted, but there's at least something now interesting that has happened. Take a look at the value 97. Where did 97 end up? In the very last spot. What is the biggest value in the entire list? 97. So in other words, going through the list exactly once ended up basically finding the biggest number, and what it did is it kind of worked its way to the back. Okay, because if I go backwards for a few seconds, I mean, take a look. This is what it started like in the first place, and you see what happened is I found the 97 here, so I flipped it. I pushed it up here, I pushed it up here, I pushed it up here, and what ended up happening was it kind of worked its way to the back. Okay, and that's really, really cool. Now, a couple of things I have to warn you about. How many elements are in the list? Not a trick question. Okay, there's 7. The biggest index is 6. And you'll notice that in here, right here, when I did this thing, I said for range and length of data minus 1. Remember what you have to do, because I'm comparing one value against the next value, I can't go right to the end, because what I'd end up doing is I'd probably try to pick up and compare the element in position 6 against the one in 7. That's why I had to stop one thing early. All right, but my list is currently not sorted, all right, because, I mean, there's a good example in there, 85 and 77. Okay, yeah, so how do you fix this? Well, repeat the entire thing again. Okay, just go back to the beginning and start asking all the same questions again. Are those okay? Well, yeah, that's on its own is okay. These ones right here? No, so again, flip them around. Okay, these two, are these good? Yeah, it is, so we leave them. These two right here? No, so again, we flip them. We compare these two, and again, also no good, so we flip them around. Now, at this point right here, I kind of run across this very peculiar, really peculiar thing. Do I need to compare 95 and 97? And the answer is no, because we already know 97 is exactly where it needs to be. Now, if I went and I compared it, you know what, it's not a big deal. I won't find that I have to switch anything. So what I did was I left out that step. It doesn't quite match the algorithm here. Okay, it doesn't quite match the algorithm that's here because things are a little bit more efficient on what I'm doing compared to the algorithm. And the reason for that is because you would not believe the amount of pain it takes to make an animation like this in PowerPoint. Okay, good challenge for you, make one. Then you'll find out why I tried to be as efficient as possible. And that's why there's only 6 or 7 elements in this list, is because any more was driving me insane. All right, is my list sorted? And the answer is no. I've got problems, like for example, 85 and 18. Okay, so I mean, if I have problems, go back to the beginning, do the whole thing again. Oh, this is pretty repetitive. Yeah. Remember one thing that I said, sorting is a pretty lengthy operation, not only for me, but it's also for the computer. All right, here we go. We compare the 14 to 77. Yeah, we're good. 77 and 85, no problem. 85 and 18, whoops, okay, problem. So you know how to fix it? Do this one. All right, next one. Yes, I do compare this because I haven't reached there. And 85 and 90, yeah, it's in good shape. Do I need to continue on with the last 2 comparisons? And the answer is no, because we already know we've got 2 things in place. If I went on and asked, I would be asking, is 90 and 95 okay? It is. And 95 and 97 okay? Yes, it is. It wouldn't wreck any of the algorithm. It would just take a couple of extra steps in my animation. All right, and again, Am I finished? And the answer is no, I'm not. I got to keep going. Really? Again? Yeah. I'll talk about how many times in a few seconds. Okay, here we go. This needs to be, that's going to be left alone because 14 is smaller than 77. And there you go, there's a problem. Those two need to be switched. And this one right here is not a problem. And again, I'm just going to leave out the rest of them because everything else is going to be in order at this point. All right, so am I sorted yet? And the answer is yes, but the only reason why we know it's sorted is because we have eyes. The computer doesn't. Here's what the computer would do. The computer would go back to the beginning and ask the same questions again. Are those two okay? Yes. Are those two okay? Yes. And then I wouldn't have to go any further because I know everything else afterwards is okay. Here's the rule. You can stop in the following case. If you go all the way through and nothing has to be switched, you're done. Okay, that's the rule. So if you're going through and you realize that everything is exactly in the right order, there's no reason to repeat it. But if you switch anything, you have to go back and you have to go through the entire array, or the entire list again. Sorry, I keep calling it array from my Java course. So keep going through the list over and over again. How many times do I need to go through? Well, if there are 10 elements, I have to keep repeating this thing, well, 10 times? Actually, you can get away with 9 times, but yeah, 10 times. It's the easy way. So if you have 100 things, you have to go through the list 100 times. Okay? And guaranteed, after 100 iterations, you will be finished. The code that I've written here actually does this. You see, I've got two loops. I've got an outer loop, the I loop, so sorry, I'm using generic things. Everything that you find on the internet will have exactly this. The outer loop is repeating the process over and over again. How many times? Well, as many times as there are elements. So if there's 1,000,000 elements, the outside loop is going to repeat 1,000,000 times. The inside loop is me comparing the two values side by side. If I ever find them out of order, which is the question if data j is bigger than data j plus 1, so if my value is bigger than the next one, well, I make a copy of j, I overwrite j with the other one, and I take this and I put it back. Okay, and that's the typical switching. Okay, so there you go. That's a bubble sort. Okay, it's pretty easy to understand. It's a lot of operations. Yeah, that really is a lot of operations. Can we do better? And the answer is, yeah, you can do better. That's just a short answer. The long answer is take the data structures and algorithm analysis course because it's that long. There are some very, very clever techniques that are just way beyond anything that we can cover in this course. But this is one of the easiest algorithms. And you know what? If you ever had a bunch of stuff that needed to be sorted and you had enough time, the code is pretty simple. Okay, the code is pretty simple. You set up a loop, you go through the list a whole pile of times, and then within that, you just check the two, and if they're out of order, you switch them. Okay, that's all you need to do. You repeat it n times, and you've got yourself a sorted list. All right, and of course, what can you do with your sorted list? Well, now you can ask questions like, what's the smallest number? Well, I'm guaranteed it will be at data at 0. The biggest number, data at -1. I can ask for the 5 smallest numbers, the 5 biggest numbers. I can binary search this now, which is really cool. I suppose the only final thing I should say, okay, good, and it's actually here in the notes, is why do they call it a bubble sort? All right, I believe that it had to do with my description. Let me have to go back here a little bit. Okay, this is the very first thing, and notice what happened is that the biggest number, the 97, kind of made its way up to the top. And I believe that the idea was they were thinking about bubbles in water, and they thought that, okay, well, the bigger bubbles would sort of work its way up to the top first. Yeah, I think that's where the idea came from. All right, and that's what happens. So every time I make it pass through, I get a 97. Well, the second biggest number currently in the list is a 95, and if you watch what happens, it works its way up to, well, almost to the end. The next biggest number is a 90, so it works its way up to the end. There's other things happening. Then the 85 will work its way up, and then the 77 will work its way up, and then the 18 will work its way up, and then is fully sorted. I think that's where the name comes from. All right, the big problem that we have with this, and I believe that this also pops up in another slide, is how many operations does this take? Now, I've left the algorithm this way because it makes it pretty clear. Let's suppose I have 1,000,000 elements in my list and I'm trying to sort it. The loop right here, sorry, go back. The loop right here, the I loop, how many times does that repeat? Okay, so 1,000,000 elements, how many times does it repeat? 1,000,000. All right, and then, of course, the J loop is inside the I loop, which means that it repeats, well, 1,000,000 times, whatever it actually happens. So how many times, just ignore the I loop for a second, how many times does the J loop occur? Well, it goes length minus 1. So if there's 1,000,000 items, it means that the J loop occurs 999,999 times. So therefore, a statement right here, like the if statement, happens 1,000,000 times, 999,999 times. Ooh. And if you're wondering how big of a number that is, well, that's going to be an incredibly large number. So I'm talking about something like 1,000,000 times 999,999. So we're talking about that many times. That's a lot of stuff. Okay, it really is a lot of stuff. And even my little algorithm right here with 7 elements, that means that there was actually 47 steps that I had to go through. And yes, I actually made 47 layers of various colors to put together that quick little animation. Everything scattered everywhere, eventually put all together. All right, yeah, sorting is really slow, okay? But the algorithm is simple. That's good. All right, I've got another one. Okay, and this one is actually really kind of clever, but what I want to do is not this, but let me pop open this instead, okay? And I'm going to ask a couple of questions. Okay, we can even write some code for this. All right, I want to know the smallest. What is this? How do I find the smallest value?
Min.
Yeah, good. Min of data. Here, I'll even print smallest to make sure that it's there. Okay, 14, that's the smallest number. Oh, sorry, I want to change the data a little tiny bit. Sorry, I didn't quite see this. Here we go. There, now we've got it. Okay, all right, so what's the smallest value? 18, okay, good. That's what I'm looking for. Otherwise, it would have been a very boring exercise. What's the location of the smallest data? What position? Oh, okay, so I'm going to call it small lock for smallest. Okay, do you remember how to find the smallest thing? There is a method that I can call called data.index, and I can ask for the smallest. And what that will tell me is it will tell me the location of something. There we go, so it's in position number 5. Okay, now I'm going to ask you, very straightforward, okay, even though I know I changed up the diagram just a little bit. The array just a little tiny bit. It's not a diagram yet. And I'm going to leave the other one. All right, and I'm going to ask, is that sorted? Of course, the answer is no. All right, suppose you couldn't actually see it, okay? Pretend you couldn't see the data, because this is what a computer sees. Right? So a computer doesn't see everything. I mean, it can, but it has to look at individual things. Just give me a second. I've got an app here which is pestering me to do something with it. All right, and this one back to here. All right. You can't see the data because, well, it's being obscured. Based on the 2 pieces of information that I printed, can you tell whether or not the list is sorted? And I can tell you, no, it isn't. Why? The smallest value is 18.
Position 5.
And it's at position 5. Where should the smallest be?
In the first position.
It should be in the first position. Okay, so this is the idea behind the second sorting algorithm I'm about to show. It's called a selection sort. All right, here's the idea behind it. What you do is you go through the list and you find the smallest item and you put it at the beginning. Okay? You just switch the 2 around. In fact, if you wanted to, here, I can do this. I can do one thing here. I'll have to undo this. We get the smallest location, and I could say temp at data 0, and I could say data at 0 could be equal to the smallest, and then I could say data at the SM lock is equal to temp, and I'm going to print data before and after. Okay, here, we'll do it right here. And I'll print up one of my famous little separators so that we have less confusion. All right, so I'm gonna find the smallest, I'm gonna find the location of the smallest, and then temp is equal to data 0 is equal to the smallest, and, oh, sorry, not smallest, temp. No, smallest. Smallest is what I'm looking for, and then I'm going to print the data again. All right, so there we go. There's the before, and there's the after. You see what's happened? The 18 and 24 have exactly switched. So I know it's not sorted yet, but it's a little bit more sorted. Kind of in the same way when I switched the two things around. It's a little bit more sorted. There was less problems. And right now I've got a less problem. Okay, I'm not sorted yet. What am I going to do? Well, I'm now going to say something like this. I'm going to say rest of list. And I'm going to go to the data, let's see, 1001 colon, and I'm going to print rest of list. All right, what does that show? It shows everything else except for the first spot. What am I going to do? I'm going to repeat the same operation again. I'm going to flip things around. Yep.
Can we do this way of switching around the smallest number to the position, but as a loop, so it continues taking the...
Yeah, of course, that's what you're going to do. So then you're going to move to the next position, find the next smallest one, put it in place.
Yeah.
And that's exactly the algorithm. Okay? All right, so here's the algorithm. It's not using list slicing, but I just want to show this list slicing that, yeah, now you repeat the operation again. All right, so again, just ignore the code. I think the picture is probably worth a lot more. Then I can talk about the code afterwards and what it's doing. Okay, so the idea is that you go through the list looking for the smallest element and then drop it into position 0. Then you look at position 1 and you find the next smallest thing, you put it in position 1. You find the next smallest from the remainder of the list and put it into position 2. All right, so here's what's going to happen. Now, my picture is maybe not the best, but here's what we're going to do. This is the one that I'm interested in, is 14. What I'm going to do is I'm going to go through the entire list and see if there's anything smaller than 14. We know that it's not there, but the computer doesn't. Okay, so we have to go through. So we check it against 97. No, not smaller, not smaller, not smaller, not smaller, not smaller, not smaller. So therefore, the smallest value is the number 14. It's located in position 0. So what I'm going to do is I'm going to switch whatever's in position 0 with whatever's in position 0. Well, that's what the algorithm's going to do. Yeah, it's kind of silly because that's what we're going to put in place. And there we go. Now it's locked in place. That was the smallest one. All right, now I'm going to repeat the same operation, but I'm going to start searching here. And I'm going to say, okay, let's find the smallest in everything that's left. Okay, so 97, that is the smallest I've seen so far. But, 85, that's smaller. That's smaller. That's smaller. That one's smaller. And that one's smaller. But, of course, this one right here was the smallest. So what do? Well, I'm going to take, so there you go, that's the smallest. I couldn't remember which step I put this on. And I'm going to take the 18 and 97 and switch it. Okay, and I continue. All right, so now I'm going to search for the smallest thing in the rest of the list. So I got the 85, the 77, the 95, the 97, the 90. Okay, out of all of these, which was the smallest? 77. So this is the one, and flip them around. All right, now I'm going to repeat the same thing again. Which thing am I going to find that's the smallest? Okay. The 85 itself was the smallest, so yeah, it just stays in place. All right, next one up, find the smallest thing. It's a 90, so those two are going to be switched. Go through, find the smallest item. It happens to be that one, switch it, and okay, I guess we're kind of silly at that point because there's nothing left to do. All right, is it faster? In some ways, it's a little bit quicker. It definitely is less switching around. Trust me, putting together this animation was slightly better, but not by a whole lot. Okay, and it all has to do with simply which things. I was lucky and 14 happened to be in the correct place, but really it didn't really do anything extra. Generally, there are less switches, generally, but not always compared to a bubble sort, but really it takes about the same amount of time. Because if you look at the algorithm that I've put in here, okay, once again, it's a loop. But it's not just a loop, it's a loop inside a loop. Okay, and these are the things where you have to multiply things together. And notice what's happening is, yeah, I'm going in range of length data, and I'm going in range of length data. I know it's a little less inefficient because it starts at I, but I am going through the entire thing. So yeah, it's kind of similar to before. If you have 1,000 elements, you have to end up doing the loop kind of like 1,000 times 1,000. That is the stuff we talk about in the data structures course, but we don't worry about it here. But I think as long as you realize that, yeah, okay, it's kind of slow. Okay, there's a lot of operations going on. That's an important thing. And of course, if you understand what's happening. All right, so here we go. So what is this actual code? Well, hopefully you recognize the code from here to about here. Okay, so the code from here to here, that is finding the minimum. That's the usual thing. What you do is you keep a variable called smallest, and you go through each of the items. If you find something that's smaller, you replace smallest with whatever that value is. I just have to keep track of the smallest location as we go. And then finally, after I found the smallest, well, then I end up switching the two things around. I've printed the data just so you can see how it's processing. I suppose what we could do is we could run that piece of code just to see what it looks like. Okay, but we even have a small bit already. Here's the progression. You can see what happens is, hey, the first time through, the 14 gets put in place, the next the 18 gets put in place, then the 77, then the 85, then the 90, then the 95, then the 97, and finally we've got everything sorted. So it's a different algorithm. As I say, it isn't like remarkably faster. It's a little bit more efficient because the bubble sort tends to do a lot of flipping. But again, it's not an impossible algorithm. Okay, because it's really based on things that we've done before. If you wanted to, you could even implement this using list slicing, and you could use the smallest function and so on. It wouldn't make it faster, but it might make it a little bit easier to read. Okay, so there you go. There's the second algorithm I want to talk about. Okay, oh, and now I've got to go through. Now you can watch in amazement as it happens again while I get to the next page. Okay, so what do we got? Okay, finally sorted. And what comes next? Okay, next there's a little page about the sorting speed, and yeah, these simple algorithms are kind of slow. Computers can obviously sort things really quickly, that's good, but strangely enough, I mean, okay, the other day I ran 1 million elements sorting, and it only took like a couple of seconds to do. I remember back when I first started in programming that sorting a couple of thousand items used to take several minutes. Obviously computers are faster now, so therefore you don't need anything faster. Actually, yeah, you still need it, because if you start to look at, say, LLMs and artificial intelligence, the way how these things work is they have really, really, really big data sets, and they have to find things. Now, I'm not saying that they're sorting things all the time and that they're doing binary searches, but it comes down to the same idea. The amount of data that we're dealing with is still really, really big. And you saw even the other day, 1 million items searching it several times was really, really slow. It was taking several seconds, and you might need it faster. Okay, so the next question is okay, let's go back to my output over to here. Okay, congratulations, I've sorted the data. Do you want to see how to do it a little bit quicker? I mean, of course you do. Okay, I'm going to print the data. I'm going to print the data again, but before printing the second time, I'm going to say data.sort, and oh, there you go. That was a lot easier, wasn't it? Yeah, there's something built in. All right, so if it's built in, then why recovering this? Okay, well, I've said it before. The course is called Introduction to Computer Programming, not Python. Okay, not all languages have this built-in sort stuff. A lot of them do. That's good. And if you ever need to sort something, by all means, if you can use the built-in stuff, then you do it. However, why might we need it? Okay, well, the reason why we might need it is because sometimes we have some data that just doesn't fit. Okay, and what have I got over here? All right. I'm not sure if you've been through the lab yet this week. Okay, if you have, you're going to run across this big, long, oh, that's not a list. Well, that's not helpful. You can't sort a dictionary, by the way. Why can't you sort a dictionary? Oh, so that's a question I can ask them on the final exam. Why can't you sort a dictionary? Yeah, because it doesn't have an order. Good. Okay, that's why you can't sort it. What you could do is you could turn it into a list and sort it, but you can't sort it directly. You can sort lists, and that's really about the only thing. Can you sort a tuple? There's a funny one.
Can you sort of tuple?
Well, not directly. Okay, why not? Because you can't modify it. But what you could do is you can convert a tuple into a list. It's very, very simple. It's just list, and you pass in the tuple. Then you can sort the list, well, assuming that you have the algorithm on hand. Then you can take the list and you can turn it back into a tuple, and now you have a sorted tuple. All right, here we go. And right here, excellent. Now I got a list, so sorry about that. I should have converted that already. I've got a list of books. Perhaps I would like to sort this. What do you mean by sort? I mean, there are three things in here. I mean, do you mean sort it by author's name? Do you mean sort it by the title? Or do you mean sort it by the price? Okay, well, we'd have to make that decision. Okay, which one are we looking at? All right, well, let's do this. Let's sort it according to price. Right? Because we want to see the cheap books at the top and the more expensive ones at the bottom, because maybe we have just a small amount of money and we have to find out what we can afford. All right, so I'm not going to put it here. Whoop, I'm going to put it right down here at the bottom. Wow, that's not helpful at all. Give me a second, turn hiding on. All right, and here. I'm going to toss this right down at the very bottom. Maybe one step smaller. Okay, sorry. All right, let's sort it. Excellent. It's called books. Books.sort. Print books. Well, that's got to be easy. I mean, we can obviously call sort on a list. Oh, wait a minute. No, we can't. Because it says right here that it can't perform the less than operator between instances of dictionaries and dictionaries. Because what it's trying to do, what the algorithm is really doing, is it's trying to find out if this is less than this. Okay, well, that's if it was a bubble sort. Okay, and you can't do that. But I want sort because I don't know the algorithm.
What if we said books that sort price instead?
Yeah, okay, so that, luckily, the sorting function does allow you to sort things, really complex things, covered on Monday, okay? But for right now, hey, we've got an algorithm. Okay, somewhere in here, sorry about this, let me pull up this, and we've got a simple algorithm. Okay, a bubble sort is pretty unpleasant, but you know what, it works. Okay, I'm gonna steal it. All right, here we go. And I'm just gonna fix it so it works in this case. All right, the first thing is it's not dated, now it's called books. We go to books. Okay, I think I can copy and paste this. Okay, we'll get back to that in a second. All I'm gonna do is just replace this all the way through, and this, and this. Okay, so there we go. So instead of the built-in sort one, I'm going to try running my own. Okay, let's try running my own. And this says that the greater than symbol is not supported between instances of dictionaries and dictionaries. You see, the problem is that books at a given position is a dictionary, and you can't compare them. But what I could do is I could certainly compare, say, the price to the price of the next book in the list. And now, suddenly, this works. Now, that's going to be hard to see, so let me write it out this way. I'm going to say for x in books, print x, and I think it'll be marginally easier. Okay, maybe not because there's too many pieces of information. I'm going to print x's price. Okay, sorry, there you go. There's only the price. Yeah, those things are sorted. So you see, it is possible. Oh, what if I wanted it the other way, like having all the big numbers first? There you go. Yeah, that's pretty simple. What if I wanted to sort according to the author or to the author's name? Okay, well here we go. Let's sort it according to the author. Right now it's author's name. We'll extract one of those. Okay, I should have picked some easier data. There you go. Is that sorted? Well, whatever that means. No, that's not sorted because I sorted according to price, but if I wanted to see a sorting according to author, I could simply add authors, and of course not the full author, but the author's name. Okay, it's getting a little more complicated, but you notice the algorithm hasn't changed. It's exactly the same algorithm. All I need over here is an author name. So here we go. Here's an author. Yeah.
We can put this in a variable, right?
Yeah. Yeah, you could put that into a it would probably make this a little bit easier to read. Okay. All right. Is it sorted now? Well, yeah, according to alphabetical sorting, yeah, it's done this way. What if I wanted to have the people with the long names first and then the short names later? Okay, no problem. These are the names, so all I could do is I could ask for the length of the name. And sorry, this is now going off the edge. Okay, you see a smaller size font would be much better, but take a look at this. See, now it's kind of cool because now we got the short names first and the longer names afterwards. In other words, having access to that sort algorithm is actually really convenient. You can't use it directly copying and pasting, but with a little bit of modification, yeah, you can actually still get the same algorithm to work. And I've said this before, it's not, how do I know this code? It isn't memorizing the code, it's memorizing the patterns. And that, of course, is a very important pattern. Okay, let me get over to see what else I've got in here. Okay, so I know these algorithms. We'll just leave this one up, and I'll wait for the excitement to die down about the sorting. Okay, so sometimes you have to sort complex information, and you might end up with a language where sorting is not built in. All right, true. Okay, there's a whole pile of really cool sorting algorithms. They're really difficult to understand. They're kind of difficult to implement, but I was all for these really complex things when I was going through university. I remember being in second year, and we had this huge data set, and I ran something called a radix sort, something we don't cover even in my data structures course. All right, and what happened was, yeah, I implemented the radix sort, and it was like 50 lines of code. All right, and somebody else did a bubble sort. And of course, I was like, look how slow that is. But interestingly enough, the instructor did say, yeah, sometimes you just need something sorted. And even if it's a simple little bubble sort, at least it worked. And you know, okay, if you're interested in slow programs, great. I was interested in having full speed. But in any case, so built-in sort functions, yeah, they are here. You can sort things. In other words, if you have simple lists, like lists of integers, it just works. Yeah, just list.sort. Let's go back and take a look at this. Okay, but it just doesn't work for really complex things. No, here we go. We'll grab, I'll just make up some data. Okay, here we go. Data is equal to, okay, maybe it's like some test scores or something. Okay, print data, data.sort, print data, done. Okay, excellent. That's pretty easy. I mean, the class goes until 3:20 if you want to take that long. I don't have that many slides left, but I can certainly wait. Okay? Yeah. If you need to chat, door's out there, no problem. Okay, deal with attendance. The lecture recording, as long as nothing happens, will be uploaded. It's no issue. Okay, so just please don't be in the room bothering everybody, including me. All right, so here we go. The sort something, pretty straightforward. It's just sort. What if I want them, say, in reverse? Okay, well, there's some options built in. There's one called reverse is equal to true. Ooh, but that's not how you spell true in this language. Sorry, it's how I spell true in another language. Yeah, it flips it around so biggest to smallest. Yeah, very, very convenient. For a list. There's another one that I have to show you because this one is sometimes has to be used. I'm just going to call it temp is equal to sorted. There's another function called sorted, and I'm going to print temp, and let me clear the output and take a look at this, and you go, wow, yeah, that sorts the data. What's now the difference between data.sort and sorted? Well, it has to do with what happened to data in the first place. Okay, so let me print sorry, I'll put it here. I will print one of my little horizontal separators, and I'll print data afterwards, and you'll see what happens is the original was never touched. Okay, sometimes you want to hang on to the original value, so that's what you use sorted for. They both work the same way. And does it use does it use bubble sort or selection sort? It uses neither. It's usually implemented using something called quick sort, which is not something we cover here. It's a little bit more difficult to understand, like way too difficult, so we don't cover it. Okay, that's not the purpose. All right, so what can you sort? Well, basically, you can sort anything as long as it can be compared using, well, actually, I shouldn't have said less than, I should have said greater than, because you saw when I tried to sort a list of dictionaries, it said that, ooh, I can't deal with the greater than. Okay, so anything where you can compare two values to see if something's less than the other, then you can do it. So therefore, you can convert, or you can sort a list of integers or floats, or a combination. So you put some floats, you put some integers, they compare without a problem. You can sort a list of strings. What else can we do? Ooh, well, let's ask it this question, because this might be kind of fun. Okay, print the following. Okay, what does that mean? I don't know. Maybe it doesn't work. Oh, it says it's true. What? So false is less than true. Yeah, generally here's the way how most implementations in a language work. The word false is usually the number 0, and the word true is usually 1. So yeah, false probably is less than this. So therefore, if I had, say, a list of true and false and false and true and false, and I did something like this data.sort, and I print the data, would the sort operation work? And the answer is yeah, actually it would. It would put all the falses first. All right, so that's one thing. All right, next one up. Okay, what about hello, goodbye, cat, dog? Okay, can we sort that? And the answer is yes, you can, because you can compare two strings. We've talked about it before. It's compared using lexicographical ordering, which is basically dictionary order. So cat comes before dog, not because cats are smaller, but because the letter C comes before that. And if I include something else like catapult, okay, if you sort that, yeah, that would come after cat, because in a dictionary, the shorter words come first, okay? And the only thing that's a little bit bizarre out of this is that if you were to spell dog with a capital D and sort this one, you'll actually find it shows up before everything else, because the ASCII value of the letter capital D is smaller than. Okay, don't worry, you don't have to memorize that fact, but you should know that sorting things sorts it alphabetical, okay? Yeah. Ooh, okay, that's a nice one. Okay, so let's find out. Hello, goodbye. Okay, let me get rid of this one so it's less of a trouble. And what happens if you stick a 45? Now, the thing is that if I ask, where does a 45 go? I mean, I don't know, is 45 smaller than a cat or bigger than hello? Well, it's actually impossible to compare. Okay, and that makes a lot of sense, and it says right here that the less than is not supported between int and string. So as we go through and you try to do these comparisons, it doesn't work. However, if you wanted to, you can turn it into a string. Okay, now you could actually sort it. It would show up at the beginning because the digits actually show up before everything else, which does bring up a very, very nasty little problem. And I think I kind of described this once as a demonstration, and that is if I put the number, let's see, 45, and I put the number 21, and I put the numbers, what should we have, 32, and oh, by the way, duplicates are not an issue in here, 21, okay, it'll show up in the right spot, and 123, and I ask you, if I sort this, which one will show up first? Yeah, it'll be 123. Okay, and the reason for that is because now you're comparing strings. Just watch out for that. So, yeah, there could be trick questions. I think I've tossed this in before, but now that you guys know, I can't ask anymore. We did in a Kahoot one day. Okay, that's, I think, where we ended up seeing it. All right, so what can you sort? Well, basically anything as long as it's not mixed. If it's mixed incompatible types, no chance. Okay, sorry, over here. I think I got like one slide, and then we will be done for the day. So we'll actually finish a bit earlier. Oh, string sorting, we just did it. Excellent. All right, and of course, well, the bizarre thing is, yeah, it has no idea how to read these 1, 2, 3, 4, 5 when it's written this way. And even if it's digits, it sorts it alphabetically, and the character 1 comes before everything else. That's how it ended up in the front. So sometimes you end up with some really bizarre things when people sort things. Trust me, this happens all the time. All right, so there we go, we're done. All right, so out of all of these, what's the really important things? Okay, because that's always the question, is like, what do I need to know for the test? Right, well, I guess it's a legit thing. For the lab test, I'm not going to ask you to sort anything. Okay, so that's good. For the final exam, would I ask you to sort things? I guess it's fair game now. Do I have to implement the bubble sort? No. You can use the built-in sorting. Does that mean that I don't need to know the bubble sort at all? I have asked questions before about the bubble sort, and I suppose I could ask you to maybe as a short answer say, okay, describe how the bubble sort works, or describe how the selection sort works. That would certainly be fair game. Be a little bit different, because normally we're used to dealing with multi-choice questions, but I suppose as a multi-choice question, I give you a piece of code and say, what type of sort is it? That would be fair game. Okay. Because, I mean, now we've got at least a couple of sort algorithms. Should you memorize it? You know what, I think just especially if you happen to be in the IT field, I think you should probably memorize the bubble sort, because well, it's not that difficult. And every now and then something pops up and you need to sort something, and that's kind of the quickest one. You don't have to look it up. You don't have to go ask ChatGPT how to do this. And if you happen to not know how to use the sorting function that's built into the language for sorting something complex, it can get you out of a bind. Okay, when am I going to be put into a bind? Well, on a test. Okay, yeah, so that's useful. And yeah, as usual, if I say to sort something, yeah, you use something that's built in if you know how to use it. Otherwise, well, you implement it from scratch. Okay, but it's what I've said before is, hey, if I've got a list of integers and you want to add up all the values, you have two approaches. You either iterate through all the values or use sum. Okay, yeah, you will always use sum. You'll never do it the other way. Sometimes I get students who do that on lab tests where they don't use sum and they add everything up. It's fine. Yeah, there's no issue. I might just highlight it and say, hey, don't forget that there's a sum function, but hey, it is here. All right, 253. Hey, good news is it's a little short. Bad news for me, I'll make sure it's longer next time. So don't come back.